todavía me falta.
Paco.
Vale. Donde prefieras. Buenos días a todos, gracias por venir. Se va a proceder a la lectura de la memoria como candidato a doctor. El candidato es Ismael Ben-Yelun y el título que está escrito ahí es Topology Optimization and Data-Driven Approaches for Functionally Graded Metamaterials. Hay una razón legal por la cual el secretario de la comisión va a leer un conjuro que hay que leer.
Bueno, bien. De acuerdo con los artículos 29 y 30 del reglamento de la UPM, la tesis doctoral se evaluará en el acto de defensa que tendrá lugar en sesión pública y consistirá en la exposición y defensa por el doctorando del trabajo de investigación elaborado ante los miembros del tribunal. Los miembros del tribunal deberán expresar su opinión y formularán al doctorando cuantas cuestiones estimen oportunas. Los doctores presentes en el acto público podrán formular cuestiones en el momento y forma que señale el presidente del tribunal. Finalizada la defensa y discusión de la tesis doctoral, cada miembro del tribunal formulará por escrito una valoración sobre la misma. El tribunal emitirá un informe y la calificación global conferida a la tesis de acuerdo con la siguiente escala: no apto, aprobado, notable y sobresaliente. Cada miembro del tribunal, bueno, estos son dos párrafos que ya no se aplican, porque para que la tesis tenga mención cum laude es necesario que el tribunal vote. Debido a que el profesor Chinesta está en París, esa votación se va a hacer mediante una plataforma que se llama Doodle, mediante la cual cada miembro del tribunal puede votar anónimamente y al final pues se sabrá si la tesis tiene mención de cum laude.
Bueno, tengo que decir que el final no es hoy. Es decir, se va a saber cuando la comisión de doctorado de la escuela descubra los votos y si hay unanimidad concederá el cum laude. Yo pediría al candidato que emplee unos 50 minutos, pero es una petición. Es decir, no pasa nada si se emplea más o menos tiempo sobre eso. Como ha dicho el secretario, el profesor Chinesta va a seguirlo online desde París. Y por lo demás, puedes empezar cuando quieras. Gracias.
Members of the committee, rest of the audience here today, thank you very much for coming. My name is Ismael Ben-Yelun, and for the next 50 minutes, I'm going to present my Ph.D. thesis titled Topology Optimization and Data-Driven Approaches for Functionally Graded Metamaterials. This thesis has been submitted for the doctoral degree in aerospace engineering and has been conducted under the supervision of Professors Montáns and Saucedo-Mora. Here is an outline of the presentation of the talk that I will give you today. I will start with an introduction of the topics, reviewing the state of the art, and setting the objectives of this thesis. Then I will move into the main part of the presentation, 2 chapters containing the publications result of this thesis, and finish with some conclusions and future works. I like to describe the title of this thesis as this 3-leg stool, each of the legs containing one of the topics to cover. Topology optimization, the field within mechanics that aims to find the best structure according to central criteria. For instance, the minimum mass structure or the stiffest solution. In fact, this stool over here with these shapes resembling nature can be the result of a topology optimization algorithm. The second leg is related to data-driven approaches. In this digitalized world in which hundreds of gigabytes of information are available, we build surrogate models, that is, less complex models of the reality that learn from those data and can perform some operations in a more efficient way. The third leg is related to functionally graded metamaterials. But what are metamaterials? We know that ages of history have been changed by technological advancements in materials. Stone Age, Iron Age. Some authors claim that we now live in a molecular era, enabled thanks to the micron resolutions, enabled thanks to the 3D printing techniques. So in this context, the metamaterials began, and they are defined as microarchitected materials that can exhibit unique properties compared to the bulk materials that they are made of. On top of that, they can be functionally graded, which means that their equivalent properties can vary across the domain. Now let's give a quick example of every of the topics. So let's say that for topology optimization, we have this domain omega with these boundary conditions. If we run a minimum compliance optimization algorithm, this is the cantilever beam that we would achieve. In terms of data-driven techniques, an example that I like, it's the image recognition by artificial neural networks. So this model can learn from data, in this case, handwritten digits, and can identify this image over here as an eye, replicating the phenomena that is happening in our eye. And lastly, as I was saying that metamaterials can exhibit unique properties, one of those properties is the ability of being auxetic, which means having a negative Poisson's ratio. Now, let's review in a little bit more of detail every of the topics and setting the state of the art, starting with topology optimization. As a mathematical optimization problem, we will minimize an objective function, for instance, the compliance of an structure, subjected to some constraints, the linearized equilibrium equation, and some other constraints like volume in compliance minimization problems. We will typically consider linear elastic isotropic materials, and on top of that, we will typically consider penalization techniques, which means assuming an exponential law relating the density of an element and its stiffness. This is assumed in the solid isotropic material with penalization, the SIMP scheme, which is one of the most famous topology optimization algorithms, which is gradient-based. But there are other techniques like ISO that don't require the computation of sensitivities, and they are simpler in that sense. This idea of being evolutionary or hard-kill will be exploited in the second part of this defense. Sigmund and Maute highlighted in the review paper 10 years ago some of the challenges that topology optimization have to face. For instance, the ability to deal with multi-scale problems and hence computationally expensive problems. And also, the ability to deal with complex boundary conditions, mixing force and displacement impositions. But on top of that, we identified that these algorithms are typically targeted at global requirements. For instance, the global compliance of a structure. And we are missing the opportunity of targeting local objectives, implementing functionally graded metamaterials. By the way, I'm continuously talking about topology optimization, but let's frame it within structural optimization. So basically, we have size optimization, in which the thickness of the members of our structure are the design space. In shape optimization, the boundary of that domain is going to be our optimization variable. And lastly, in topology optimization, every element of my finite element discretized mesh is going to be an optimization variable. Now, let's move to the data-driven techniques. As I was mentioning, there are plenty of data available in order to build our surrogate models that can bypass expensive evaluations. And in our case, that data from which these models will learn is going to come from either simulation or experiments. So far, when we are solving a part or a component in our computer, we are building a so-called virtual twin of the reality that takes into account the physics. If instead of that, we fit, say, an artificial neural network with data coming from simulation, we would build a digital twin. So the concept of hybrid twin, mixing both realities, has appeared recently, in which we are building less complex models of the reality, and hence more efficient, but also considering the physics. There are plenty of algorithms available in these techniques, from classical machine learning algorithms, from deep learning algorithms, for example, this artificial neural network. And for computational mechanics approaches, I highlight this review paper. And some of the cases are continuum-based, like YPY, or physics and structure-based, like physics-informed neural networks. These sometimes black box models have to be explainable or interpretable because we have to implement them in a regulated framework as engineers. For instance, in the aerospace industry, in order to, we should certificate every single method, software, or tool before including it in an actual aircraft. In this slide, I saw a couple of examples of graph neural networks and advanced architecture that I will explain in the third part of this presentation, applied to material sciences, for instance, we know that the structure of materials are actually graphs, so we can compute artificial neural networks on those. And another application of GNNs with physics-informed neural networks, the flow around the city. Now, let's move to the field of the functionally graded metamaterials. So first, we need to define what a representative volume element is. We know that atoms form materials, this yellow block. For instance, the aluminum. We know the mechanical properties of the aluminum. But if we go one step further and build these lattice structures and then stack those cells into this blue block with some homogenization methods, we would have built a representative volume element in which we will compute effective mechanical properties. In my case, I will focus on the effective Young's modulus and the effective Poisson's ratio. So now, if I discretize my domain in these blue blocks over here, instead of having to compute all the properties in every yellow structure, I will rely instead on the mechanical properties of the RVE, with the consequent saving in computational time. On top of that, they can be functionally graded, which means that, for instance, in this case, we have a stiffer behavior longitudinally in the left-hand side, up to a stiffer behavior in the transverse direction in the right-hand side. Since this problem comprises several scales, it's a hierarchical problem, the multi-scale problem arises, and it is expensive. Sometimes it is solved via FE square approaches, which are computationally expensive, as I was mentioning. And lastly, let me show you an example of the Eiffel Tower, which I think is a nice definition of what a metamaterial is. We know that the Eiffel Tower is built out of iron, and we know the mechanical properties of the iron. But if we were able to test the whole Eiffel Tower and, let's say, estimate the equivalent Young's modulus, it's going to be different than that property from the iron. So I think that's a nice definition of what a metamaterial is. I have to say that when I started researching about those topics, I was kind of skeptical about this, so I went there in order to test it. So this is a picture that I took from my research stay at Paris Archimedes Institute of Technology. Okay, now that we have reviewed in detail all the topics that I will cover during my PhD, we have identified some of the key points that motivated our study. We know in the literature that there are a lot of topology optimization algorithms, even for multi-structural optimization processes. And in some cases, they are targeted at local requirements, like, for instance, local stiffness here, or local stress constraints in the constraints. But when we take a look to the macro-scale problem, we always see that they are targeted at global requirements, for instance, the global compliance. So we identified that novel topology optimization algorithms for functionally graded metamaterials targeting local behavior directly in the macro scale are needed. In the literature, we can also find this kind of data-driven surrogates in order to be more efficient in the micro scale. But again, if we take a look at this kind of algorithms, recent papers, recent publications, we will see that the global objective function is as I was saying, a global variable, and not a local one. So considering this, let's put the methodology in a concept map. We want to develop topology optimization algorithms that obtain functionally graded solutions, like this one over here, because this is a Young's moduli distribution. And we want to generate metamaterials or create that can behave as these solutions yielded by the topology optimization algorithms. But this is an inverse problem, and hence it is ill-posed. There are plenty of configurations that can behave similarly in the macroscale. Therefore, we followed two approaches. The first one, an experimental one. So taking this unit cell and assuming an exponential, square exponential law, we can actually build metamaterials out of Young's moduli distribution. And we can actually print those components in 3D printers, like this chair over here. So this would be a mechanical point of view of solving this challenge. But as I was saying, we can take advantage of data-driven surrogates. So in order to do so, we're going to first build a machine learning model able to compute effective properties in metamaterials with fixed topology unit cells. And then we will go one step further, building graph neural network surrogates in order to compute these effective properties. With that, we will have a large data set containing different lattices, and then we could perform a first step towards inverse modeling, because we can request a specific Young's modulus of this element, for instance, and then suggest the corresponding unit cell. This comes with some limitations. For instance, I'm talking about printability. That is the reason why I will focus also on robust topology optimization techniques addressing uncertainties. And these machine learning surrogates are limited to linear elasticity. That is the reason why in the last part of the presentation, I will present a machine learning surrogate accounting for nonlinear effects like fatigue damage in composites. So having said all the methodology, we can establish the objectives of this research, which are to propose novel topology optimization algorithms targeted at local requirements for functional integrated metamaterials, to build machine learning surrogates able to compute effective mechanical properties in lattice materials, with the aim of joining both previous objectives together to address multi-scale structural optimization problems. Or in a more general way, we want to provide computational methods and tools for structural analysis and optimization of functional integrated metamaterials, ultimately being able to obtain a fast and physics-based framework suitable for computational mechanics in general. Now we will move to the second part of the presentation, in which I will present topology optimization algorithms. I will present two original contributions. The first one related to those novel topology optimization algorithms targeted at local requirements, and a second for robust implementations accounting for uncertainties. Let's start with the first one. So that local targeting is going to be achieved through homogenization of mechanical variables. And the problem that we are going to set is the minimization of the standard deviation of a mechanical variable h, yet to be defined. So we will discretize our domain and define one h per element and subject this problem to the linearized equilibrium equation, and we will impose directly the boundaries on the Young's model, on the material properties. These are the expressions of the variance, the standard deviation squared, and the average value of this mechanical variable across the domain. As I was saying, h could be any mechanical variable. We will see a strength homogenization algorithm and a stress homogenization algorithm. But could be any other, like for instance, the strength of a material. Lastly, this methodology can accept either force and displacement in position, dealing with these complex boundary conditions challenge highlighted in the review paper. As for the optimization process, since Newton-Raphson schemes present problems because of the singularity of the Hessian of the objective function, we will use a gradient descent scheme with this adaptive step eta for searching the minimum. Let's start with the strength homogenization problem. So we can express the total strain energy of a domain as a sum of the energy contributions of every finite element. Assuming a linear elastic isotropic material and performing numerical integration, we can express the total energy of one element as the multiplication of its Young's modulus, and this energy over here, but divided by the Young's modulus, because this d hat is going to be the stiffness matrix in Voigt notation divided by the Young's modulus. So if we fix, excuse me, the Poisson's ratio, that means that this expression over here is not going to be dependent on the Young's modulus. In other words, we can express the average strain energy density as the multiplication of Young's modulus and this h variable, which is an energy-like variable accounting for strength level, dimensions as well. Now let's plug this into the gradient descent definition. So after some assumptions, imposing an adaptive step and grouping this variable over here, we will reach the updated properties model. And basically, we will follow an evolutionary approach in which we will solve the equilibrium, update the properties, and in this new design point, we will solve the equilibrium again until some convergence in the total strain energy function. Our objective function is convex because of the positive semi-definiteness of the Hessian. And we will update the material properties following this formula. But how does it work? Basically, we have this update parameter for every single element. So those elements presenting an H level at the formation level higher than the average will have a positive alpha, which means that their stiffness is going to be increased, and the other way around. Since it is an adaptive step in the gradient descent algorithm, we will prescribe this parameter K, which is a smoothness parameter accounting for the step size. Let's have a look to some toy examples in order to understand how the algorithm works. So we'll start with this system with 3 springs, and we want to run the updated properties model with a sufficiently high number of iterations and sufficiently smooth parameter in order to ensure smooth evolutions. So we will start putting the same stiffness to all the members. So that means that the left-hand side is going to have twice the stiffness of the right-hand side. And by essential mechanics, that means that the right-hand side is going to have a higher level of deformation. If we plug that into the updated properties formula, that means that the stiffness of element 2 is going to be increased. Let's see some animations. As I was mentioning, the stiffness of element 2, the orange line, is getting increased up to some point in which we have reached an homogeneous deformation state. Because we know that when this element over here has twice the stiffness of these two, that means that the deformation level is going to be the same in both sides, which means that the alpha is going to be 0, and we have reached this homogeneous state. We have stabilized the compliance, and we have minimized our objective function. But what happens in other cases in which there are some elements that are not carrying any kind of load? In those cases, the homogeneous state is not possible, because there will be always elements with 0 deformation level, and there will be elements with always non-zero deformation level, reaching these kind of solutions. Once some of the elements tend to be decreased their stiffnesses, and other tend to be increased. This shows that there is a need of limits in our algorithms, lower limits and upper limits. So those elements presenting a stiffness below a certain threshold will be removed, as in a hard-kill evolutionary scheme. And the other way around, maybe we can impose, we will impose some maximum stiffness level in order to put some limitations. So what we will do is those elements reaching either their upper level or lower level will be removed or will be no longer updated in our scheme. And the homogenization will be pursued in the rest of the active elements. Now let's take a look to some numerical examples. I will start with a cantilever beam in plane stress with quadratic finite elements, and 3 3D cases with tetrahedral elements with one integration point. So starting with the first one, this is the ground structure, and our approach yields this functionally graded solution. If we compare to an unparallelized version of the sim, we can observe that we achieve a quite similar solution. And this is interesting because we are pursuing different objectives. In our case, we are minimizing or we are homogenizing the strength level, whereas in sim, they are minimizing the compliance. And yet we are achieving the same results. This other curve that I showed you with a dashed blue line represents the dual solution, which means solving this problem, but imposing the displacement, the equivalent displacement instead of loss. As I was saying, we can reach the same solution because we are in the linear region. Let's go for the 3D examples. We have this domain over here. We will restrict the displacements in the bottom face nodes, and we will impose a vertical load in the top face nodes. If we run the algorithm, this is the solution that we will get, an homogeneous deformation. This is a solution in Young's modulus. Note how those elements close to the boundary conditions reach their maximum stiffness level first. And if we compute the optimization curves, we will obtain something similar to the previous case. This is a validated example with a finite element software running the SIP and penalizing. Let me show you a couple of examples more. Here is a shear load case and a chair load case that motivated us to print this kind of components. Same conclusions might be applied. So this was a strain homogenization implementation. Now let's go for a stress homogenization. We can define a new variable h, but in terms of the complementary strain energy function. And following the same approach of minimization, we will reach this formula, which is similar but works the other way around, which means that those elements presenting a higher level of stress than the average, their stiffness will tend to be decreased. Let's have a look at how both implementations work in another toy example with 3 springs. So we know that if we run a strain homogenization, those elements carrying less load, in this case, this one because it's tilted, the green one, will tend to be removed. But if we run a stress homogenization, it works the other way around. It will increase the stiffness of this element up to some homogeneous state in stress. So every element have the same stress level. So we can say that whereas strain homogenization algorithms seek to remove all those elements that are not working, stress homogenization put all elements to work in order all the elements to share the stress level. Orthotropic extensions might be possible in this kind of algorithms by performing a volumetric deviatory decomposition on the complementary strain energy function. So taking into account that an orthotropic material has 9 elastic constants and fixing 3 Poisson's ratio, that leads us to 3 longitudinal moduli and 3 shear moduli. So we will perform an update of the 6 elastic material properties at the same time in some kind of multi-objective optimization problem. So if we run a strain homogenization algorithm in the chair example, for instance, we will reach more optimal solutions thanks to the wider design space that we are considering. So with that, that was the end of the novel topology optimization algorithm that I wanted to present. Now let's move to robust implementations. So we will apply this kind of robust implementations in lattice structures, like this one over here that I saw. So we will perform robust designs on lattice structures, as I was mentioning. And we will consider some uncertainty. In our case, we will consider material uncertainty in terms of Young's model. So the Young's moduli vector, this R, is going to be sampled from a random field with a design value, R with a bar, and a covariance matrix. And we state that those uncertainties are spatially correlated. So every time that I sample from that random field, I will obtain a different stiffness distribution. So the idea of robust implementations is not only obtaining, let's say, the minimum compliance solution, but also the less sensitive to uncertain parameters. And that is obtained by changing the objective function with a weighted sum of the mean compliance and the standard deviation of the compliance across all the different samples that one can imagine from a random field. We will use penalization and sensitivity filtering, and the objective function and sensitivity analysis will be performed through a first-order second moment approach, achieving this kind of solutions. We validated our implementation in this verification example from a paper from 10 years ago. And if we run this optimization, but only the deterministic part, which means only considering the mean compliance, we will achieve this solution. This is the stiffest solution with this maximum volume. In the other case, only considering the sigma j, the standard deviation of the compliance, we obtain a kind of different solution. Note how the material is placed in a more spread fashion in this case in order to address those uncertainties, which effectively achieves a reduction in the standard deviation of the compliance. This example over here was run with a diagonal covariance matrix, which means that every single element has a stiffness with its standard deviation, but it's uncorrelated from the rest of the elements. But how can we compute the spatially correlated uncertainties? Well, I would like to introduce this 3D printing case, which is an extrusion-based. And now let's think that we have, in this kind of processes, a sudden rise in temperature in the nozzle, which is placed in the material. That sudden rise will imply a defect on the material. And if we say that that sudden rise lasts for 5 seconds, those elements printed across that time frame will present a discrepancy and uncertainty related to their Young's models. We also know that the physical processes that occur here are heat and mass diffusion processes, which are modeled through elliptic operators or elliptic partial differential equations. So that motivated us to use Matern random fields, which are the solution of stochastic partial differential equations, which are elliptic as well. We know that the Matern covariance function has this formula, but the problem is that it is based on Euclidean distance. So in order to compute Matern random field on lattices, we will perform a finite element discretization of the previous stochastic PDE. So we now have this algebraic equation, and if we compute its variance, we will reach to the covariance matrix, or even better, the precision matrix, which is the inverse of the covariance matrix. And we proved that this precision matrix is sparse, which is an advantage because it allows us to perform efficient operations with a high number of elements. So with that, we can compute material random fields on this kind of lattices. And in order to do so, to compute the fields on these members, we will first derive the adjoint graph and then solve the finite element discretization on these red nodes. Let me put you some examples. So here we have 30 by 20 example lattices. In this case, we have a covariance matrix with a length scale of 3. See how locally correlated are the uncertainties, up to a lattice with a covariance model with a length scale of 20. In this case, for instance, the sparse precision matrix will be with more elements than in this other case, of course. And we can actually build some kind of custom. We can model those uncertainties. For instance, this is a toy example, varying from L equals to 3 to L equals to 20. Now, let's move to numerical examples. We are going to perform the BCC lattice discretization of this General Electric engine bracket. We will use a covariance matrix with a length scale of 10, which means 2 unit cells. And if we compare the deterministic solution with the robust solution, we can observe how the material is more placed here than in the deterministic case. And although the differences in the visual way can be subtle, we can note that by only increasing a little bit the compliance reached, we are almost halving the standard deviation, effectively achieving a robust design. This is an animation showing how the optimization process works. Let me note that this case over here uses 80,000 members. So far, we are able to obtain functionally graded solutions, able to deal with uncertainties. But now, let's move to data-driven approaches in order to build data-driven surrogates to compute equivalent properties and obtain this kind of functionally graded solutions yielded by the topology optimization algorithms. So I will present 3 machine learning algorithms. The first one, a surrogate computing effective properties in these lattice materials. A second one, a graph neural network approach. And lastly, a novel machine learning algorithm accounting for nonlinear effects. Let's start with the first one. Here I present you the gamma, general accepted metamaterial. It's built with unit cells with fixed topology that has been patented, and it can be parameterized with 4 geometrical parameters. Using a proper mechanical model, we can compute the effective mechanical properties, namely the effective Jones modulus and the effective transverse Gaussian ratio. So the idea is to use both input and output data in order to train a machine learning surrogate model and then predict the effective mechanical values. Let's start with the RVE definition. So we have this unit cell with these 3 geometrical parameters and a 4th geometrical parameter, which is the separation between layers. We will set the number of layers to 5, and then by varying these 4 geometrical parameters, we can obtain different configurations. For instance, note that if we change this vertical distance of the top and bottom nodes to the mean transverse plane, we can obtain from a non-auxetic configuration, and by flipping it, we can obtain an auxetic configuration, because the top and bottom nodes allow, as this image shows, for vertical connectivity between layers. The mechanical model that we will use is a linear Euler-Bernoulli beam lattice, and we will generate a data set of 10,000 cycles by varying those 4 geometrical parameters that I was mentioning. Obtaining different configurations, for instance, the conventional behavior or an auxetic one, the one that I introduced you at the beginning of the presentation. As for the equivalent mechanical properties, we will impose some displacement in the top node, the top face nodes, in order to recreate a uniaxial test. We will compute the reaction forces, and based on the Hill-Mandel principle, we will compute an energetically equivalent continuum block. And based on that, we will compute again the effective mechanical properties, the effective Jones modulus and the effective transverse Gaussian ratio, achieving different behaviors. For instance, in this one, we can achieve an almost 0 Gaussian ratio, because note how the geometrical parameters allow for that, or in this case, an almost -1 Gaussian ratio. They have the same topology, but their geometrical parameters have changed. So the idea is to build a machine learning surrogate, inputting this data and predicting these mechanical properties. So we are performing a random train test split of our dataset, 80-20, and we will use a classic machine learning approach, such as random forest, averaging 200 estimators. In order to evaluate our results, we will use the coefficient of determination, the R squared. And we note that how accurate the predictions are with a coefficient of determination in the test set about 0.996. So this is a machine learning surrogate for fixed topology unit cells. So now let's perform this step further and try to make a graph neural network surrogate to compute various topologies. So we'll start with this unit cube. We'll place some joints on the unit cube. Namely, we will fix 8 joints on the vertices, and then we will place a number of nodes from 1 to 50 inside the cube. And the coordinates of those nodes will be sampled from a uniform random distribution in order to achieve a random data set. In this example that I show you, and that I will keep during the next couple of slides, I will use this simple example with only one node. Then we will connect all the joints in order to create a lattice structure, and we will consider both a pin-jotted truss lattice mechanical model and an Euler-Bernoulli beam lattice mechanical model, and compute the equivalent mechanical properties in an analogous way to the previous case, imposing a vertical displacement. Now we are focused only on the vertical equivalent Young's models. So our idea is to build a machine learning model that can input this kind of lattices and predict the equivalent mechanical property. That is the reason why we went for graph neural networks. We will compute graph neural networks on these kind of architectures. And let me stop a little bit about how graph neural networks work in our case. So we will start with this topology. And what we will do is to perform the node embedding, which means using an artificial neural network, this blue one, the same for all the features of the node. We will input the coordinates of the node and embed and create the node embeddings of every node separately. The same idea will be applied to the edges. We can put as an input the features of the edges, for instance, the length of the members, the cross-sectional area, the base material property, and then with another artificial neural network, we will embed the edge features. So for every edge separately, we are passing the same architecture discretely. Then we will take into consideration the connectivity, performing so-called graph updates. This is comprised of 2 steps. First one, a message passing, in which we are considering for every edge the start and ending node embeddings and the edge embedding. And we will pass through a third artificial neural network architecture, updating the node state or the node embedding of the ending node. So we will apply this architecture to every edge in both directions. And then we will perform a convolution. For instance, in this node over here, several messages have arrived, so we will average those messages in order to compute the updated state of the nodes. So we can perform a number of graph updates, and then we can perform a pooling operation in order to obtain the mechanical variable to predict. This architecture works for both simpler topologies up to more complex ones. And we think that the success of this architecture is because it is replicating the underlying physical phenomenon. For instance, we know that the mechanical model, actually what it is we are solving the equilibrium of forces in every node. So maybe in this message passing and convolution, it's happening that, or the model is replicating that physical phenomenon. In this slide, I show the previous architecture, but in a graph schematic way. We are performing 2 graph updates, and these are the parameters that we are using in the graph neural networks model. So we will generate 20,000 samples for the pin-jotted truss lattices, 10,000 samples for the Euler-Bernoulli beam lattices, and here are the information about the activation functions. Considering the mean square error as the loss, these are the solutions that we are going to get for both pin-jointed truss lattices and Euler-Bernoulli beam lattices, with a coefficient of determination in the test set above 0.97. With that, we have built successfully our graph neural network surrogate. So now we can map a vast number of lattices into their equivalent configuration, or equivalent, Young's modulus. So by doing so, we will only spend 3 seconds in these 100,000 lattices instead of the 100 minutes that would take the mechanical model. It's a ratio of 1/2000, more or less. So we will put all the configurations in this plot, considering also the volume in order to seek for the lightest solution. And then we can request, let's say, 100 Jones modulus of, let's say, 170 megapascals. We will zoom that area and then pick the lightest solution. So in this way, we are performing that first step towards inverse modeling that I introduced in the methodology. By the way, in this case over here, if we compare the actual mechanical model with the surrogate model, our error is less than 1% in Jones modulus. In this topology that the level has never seen before. The previous two surrogate models were accounting linear effects. Now let's develop a novel machine learning model in order to take into account nonlinear constitutive effects. So let me introduce you the maximum entropy algorithm, which is a nearest neighbors approach, in which we will have our dataset, then a new point with its features will come, and we will perform the convex combination of that new point with the neighbors. And then use the same weights and use it in the output space with the same neighbors in order to predict the target. We are selecting the optimal number of neighbors with a hypersphere of radius h, and that h is computed by the maximization of this Gibbs type entropy, using a radial basis function, the square exponential or the Gaussian kernel. So in this example, in which these are the input features, x1 and x2, and this is the target to predict, note how this point, which is traveling along this diagonal, is taking for every point to predict a different number of neighbors, so that the energy that they are providing to perform this convex combination is maximized. Now we will use it in some fatigue damage test, specifically for composites, CFRP composites. So this data set was provided by NASA, and on top of this fatigue damage test, we are performing some measurements with a non-destructive technique, such as lamp waves. So we will take our health specimen, do some measurements with the lamp waves, then put it in the test machine, perform some number of cycles, and then retrieve it every certain number of cycles to perform more measurements. So we will note how the signal with respect to the health specimen is going to change. So those are the input features from our maximum entropy model. Apart from the constitutive data, such as the ABD matrices of the laminates, we will use this ratio between the original signal and the signal in the health component and the signal in the damage component as input features, and we will try to compute the damage, which means the number of cycles remaining up to failure. So with that, in our 1,500 data points, we will reach a coefficient of determination in the test set of 0.965, which is accurate compared to the other machine learning architectures that we are using, such as neural networks, for instance, but with the advantage of not requiring training or nor hypertuning. So with that, we have finished the third part, and we can move on to the conclusions. So let me first start with the specific conclusions for every single contribution. We have developed topology optimization algorithms homogenizing mechanical variables. We saw that strain homogenization yield functionally graded solutions similar to those offered by the unpenalized sim. Homogenizing stress, we obtain a quite opposite behavior than strains, which is also an interesting conclusion. And orthotropic extensions were possible, and it allowed us a wider design space. Talking about robust implementations, we can model physical processes by providing a physics-informed prior by modeling this covariance matrix that I introduced you in the second part. Thanks to the sparsity of the precision matrix, the inverse of the covariance matrix, we can perform efficient operations up to a high number of elements. In this case over here, with 80,000 members. As for the data-driven part, we developed a machine learning surrogate able to predict equivalent mechanical properties with fixed topology unit cells, being able to bypass classical methods such as the finite element approach, in which we have to assemble the whole stiffness matrix, inverse, and then compute the reaction forces and so on, obtaining accurate results with a coefficient of determination above 0.996. Performing this step further, with different topologies, we created a graph neural network surrogate, which had the advantage of being input size agnostic for lattices with various topologies, obtaining accurate results, coefficient of determination above 0.98, and enable an inverse design thanks to the 1/2000 ratio that we are winning with our surrogate. And lastly, I presented a novel machine learning algorithm accounting for nonlinear effects for fatigue damage prediction in CFRP composites. Since no training or no hypertuning was required, we obtained a reduction in computational time with respect to other techniques of 2 orders of magnitude, which makes this model suitable for online evaluations such as SHM, structural health monitoring. So if we take a look again to the initial map from which we started, we actually obtain this kind of functionally graded solutions and create metamaterials in this mechanical point of view. And in terms of data-driven surrogates, we are performing this first step towards inverse modeling because of the development of these surrogate models and this inverse modeling definition that I introduced a few minutes ago. Since we have some limitations in printability, we developed a robust topology optimization implementation and machine learning surrogates accounting for nonlinear effects, taking into account the linear limitations. But of course, there are more limitations than the ones that I can show you there. But that means that this work can enable future works. So I will focus on 5 future works that this study may propose. The first one is to develop topology optimization algorithms that can homogenize other mechanical variables. For instance, dissipative effects like factor energy or plastic energy. The second one is the exploitation of energy-based evolutionary topology optimization algorithms in a hard-kill philosophy by solving the equilibrium, removing some elements according to certain criteria, and then proceeding up to some convergence. There are ongoing research with another Ph.D. student of the group considering plastic effects in this regard. The third idea is to consider vibrations or dynamic analysis in our topology optimization algorithms. There are current ongoing collaborations of our research group with a national public institution in Spain. And maybe we can apply this to other kinds of metamaterials, like acoustic metamaterials. The fourth idea could be using these 3D printers that we actually have in order to fit our covariance model, and then use that robust topology optimization algorithm as a kind of second loop optimization of our functionally graded structures. And lastly, since we perform a first step towards inverse modeling, another way to go is the development of a proper multi-scale framework only relying on graph neural networks architectures that can actually suggest a whole metamaterial rather than a unit cell. So, as a final conclusion, since those are the initial objectives, since we propose novel topology optimization algorithms targeted at local requirements for functionally graded metamaterials, we built machine learning surrogate models for computing effective properties on lattices, and we join these both previous objectives together to perform a first step towards inverse modeling, we can say that novel and more efficient structural optimization algorithms and data-driven surrogates may bridge scales or may address the challenge of scales in the field of functionally graded metamaterials. And if we are able to address the challenges of multi-scale structural optimization, we will be ultimately able to deal with more complex problems within computational mechanics. Let me finish with the academic contributions throughout this thesis. So during these almost 4 years, I have worked in a total of 9 manuscripts. 7 of them are already published. And I would like to highlight this one, the third one, in MDPI materials, which earned the editor's choice of that issue. There is an 8th one, actually under second review in another JCR journal, as the rest of them. And we have a 9th one currently on archive. So we are in the process of searching the best journal to proceed with submission. With respect to conferences, I have attended to different congresses, like the Congress on Numerical Methods or Computational Plasticity, presenting works in 5 different occasions and giving the conference talk in 2 cases. So I would like to finish by acknowledging some of the institutions that have made this possible. Thank you very much to Escuela Técnica Superior de Ingeniería Aeronáutica del Espacio from Universidad Politécnica de Madrid, where I studied my bachelor's degree, my master's degree, and it has allowed me to pursue my PhD. Thank you very much to my research group, Gamosinos, Group of Advanced Modeling and Simulation of Nonlinear Solids, which I'm a proud member of. I would like to acknowledge the European project Cometas, aimed at generating a network of early stage researchers, in this case for metamaterials, and which has funded my research stays. This PhD would have been very different without the PhD stays in international prestigious centers. So I would like to express my sincere gratitude to the PIM Lab in Paris Artemetee Institute of Technology and to the Department of Civil Engineering in the University of Cambridge, from which I obtained my international mention. Thank you very much for all the insights, for all the learnings, and for all the collaborations that I take for my future research career. So I would like to finish quoting Professor Mike Shih, the inventor of ISO algorithm, in a speech that he gave when he was given an award due to this most famous algorithm. I'm passionate about two things. One is to try to solve complex problems with simple approaches. The other one is doing research that is practically useful. Thank you very much. That was the end of my presentation, and I will be very glad to answer all the questions that you have. Thank you.
Thank you. Let's tell you.
Yes.
A ver, gracias por haber seguido más.